Okay, welcome everyone. Thanks for joining this first virtual meetup. Earlier, we did bunch of in-person meetups at Samosa Chai. Um, and we're happy to have Rohit Mittal, who is an expert in lots of things, but we are going to, take his pick his brain in one area today. And before we get started, welcome Rohit. And then let me introduce Rohit. He's a founding member and a senior director at UpScale.AI. They raised a lot of money recently. I know with hardware, maybe that's not enough. Rohit might say that. But happy to see him drive the innovation again and again throughout his career. Earlier, he was a TPU lead at Google. Before that, he has a distinguished career at Intel, Stanford. He has done a lot of things, right? So it'll take the full hour if I get into all that. But I do want encourage all of you to go look at his LinkedIn profile, connect with him, and engage with him offline, right? Again, welcome Rohit. Looking forward to a good discussion today. So so we were trying to do this for a while because we get a lot of questions, especially from software engineers. I have written, a lot of early, switching code, and we always, for me, it was Ethernet and above, right? There's a packet, I get the packet, and, even when maybe I've done some ASIC architecture, but still staying that high level. But I think it's becoming important to understand a little more because Ethernet is evolving and a lot of features are getting added there, like that are stateful and whatnot. So unless you peel the layers and understand, it becomes difficult to look at any of these specs that are coming out, right? Either Ultra Ethernet or SUE and various other various specs. So that's the background for asking Rohit to help us out in a kind of demystifying some of those things. And in the with the first one will be a little higher level. It'll be, it's like it's a Ethernet for software engineers, hardware for software engineers level. But we will get into details later, right? Um, so we were trying to do it before OCP. But OCP is done. We still got same questions there. Now we are heading to supercomputing. Maybe it's a good time. Maybe it's not a bad time, right? Even if it is a little late. Rohit, before we get started, right, maybe before getting into even Ethernet, I want to kind of talk about, or maybe, take your perspective on the whole AI infrastructure, right, and put that in perspective. So we hear all this scale in, scale up, all, many kinds of scale, right? And then in that context, scale up becomes important. So maybe I'm just sharing the a slide. Hopefully, all of you can see that. Maybe Rohit, could you give us a little bit of background on what is going on in terms of scale at in AI infrastructure, maybe, and then get into scale up and why now and things like that.
Absolutely. So firstly, thanks for the introduction, Venkat. I hope I live up to that introduction you gave. But I mean, when Venkat approached me to do this, I thought it's a great opportunity because the whole industry is moving forward at a rapid pace. And the more people come together to solve really difficult problems, especially in AI infrastructure, it will make things better for everyone, right? So thanks for inviting me to talk about this important protocol, which has been like there for a long time, and it keeps evolving. Internet
Ethernet is 50-year-old last year, so
yeah,
50 years
yeah.
young, let's not say
Yeah.
old.
So yeah, this is a great slide, Venkat. Thanks for putting this together. I mean, coming down to the nitty-gritty, Ethernet started, we hear a lot of chatter about scale up. So let me first share what that is and why that is important and then we can look at scale out. What scale up tries to do is to make a lot of accelerators work as like one accelerator. That's a simple way to put it. What that means is that all of those things that we expect from memory semantics, low latency, high bandwidth, where memory is connected directly to your accelerator, we want to replicate that at a much bigger scale. So if you have like 1,000 accelerators working together, it should just appear as one machine. And in order to do that, you have to make a fabric which is a little bit more enhanced than traditional Ethernet, which has lower latency, higher bandwidth, and memory semantics, like I alluded to. So that's your scale up, right? And the mental picture you can think of is that if you have like an NVL72 rack and all of those GPUs within the rack, that's the scale up domain, at least
And
right now. Yeah,
yeah,
go ahead.
sorry to interrupt. Go ahead.
And scale out is what we traditionally viewed Ethernet as, which is where you have switches like top of the rack switches connecting different racks, and you have send receive semantics where you care about latency and bandwidth, but maybe not to the same degree as what we care about in scale up. And then as Venkat put together some slides, then now we're getting other scales like scale across, and there's some to the satellite, and then there's scale in. But for Ethernet, I think the main, or for AI infrastructure, one of the main focus areas right now is scale up.
Is
You
there
had
a
a question?
reason why there is a lot more focus on scale up right now? Is it because that becomes a building block for any other scale? First, first order of magnitude maybe, or maybe the ROI is better, or what is the reason scale up is getting a lot more focus now? Why is the chatter around scale up now?
Yeah, that's a great question. I think what has happened is that, as models have become bigger, they're not fitting inside one accelerator. And so what is happening is you need all of these accelerators to behave together to kind of function as one accelerator in a way. And that's where scale up comes in. So that's one reason. Secondly, it's a brand new market. Scale up did not exist before AI infrastructure. It actually did not exist to the level it exists right now till maybe 2 years ago when NVIDIA introduced the NVL72 rack. That's when all of this thing started taking more of getting more into the mainstream. So from both of those reasons, like its newness and its impact to take AI infrastructure or AI models forward, scale up has become much more critical.
And so maybe let's peel the Ethernet and get into it, right? So we all know Ethernet is layer two. Then because for software engineers we never looked below. So what is in L1? Or what is below that, or maybe inside that? I guess, right? But
Yeah. So that L2 layer is basically where you start doing your framing and your MAC address and destination. So that's, I think, where software engineers stop when they start looking at addresses. So below that is your more like what you need to do to transmit all of those packets over wires. Okay. And there are basically three sublayers there. There's the PCS, which is your physical coding sublayer. Then there's the PMD, which is the PMA, which is the mechanism by which you take these coded packets or coded frames and um, and you serialize or deserialize it. And then finally, you have the PMD, which is your physical medium layer, which is how you send that over the wire. So you might send it over copper, you might send it over optics. So that's your PMD. So in summary, yeah, thanks for sharing the slide. So you have the
yeah, there is a picture
P,
sometimes that might help you. Yeah.
yeah, yeah. So that's your layer one, which I talked about, the PCS, the PMA, PMD, and they all work together to take your frames, which have been generated in layer two, and transmit that over the wire.
Yeah, makes sense, makes sense. So these are like, because we always talk about 7 layers, but looks like there are sub layers within a
Yeah,
layer. Is that a way
that
to look
that's
at it?
that's a good way to look at it. So this is all part of layer one, which we call the phi. Mhm.
And then kind of so IEEE defines these. Who is defining these layers? Because if the boundaries are not clear, how, because Ethernet is a greatest interoperability across industry story, right? So I'm just thinking, who is defining some of these things?
Yes. So IEEE has this standard. 802.3. If you guys are familiar with that, that is the standard body for this whole PHY layer. And they work with a lot of other consortiums like OIF and other optical and copper consortiums to kind of build partnerships and work together to bring higher speeds or different types of coding to the industry.
Yeah, I see this, Ultra Ethernet Consortium is looking at, how do we reuse Ethernet or evolve it for AI? And I see, them talking to IEEE and others. So it is a industry-wide co-design and it's a lot of effort that goes everywhere. So that's a good thing. So the other thing, right, from a software engineer's point of view, when we see hardware, when we say Ethernet, we see like a transceiver or a pluggable, and then there is a wire. So we see that as, hey, that's my Ethernet, right?
Yeah,
So where does that fit into these layers and hierarchy?
yeah. So the transceiver is effectively a physical manifestation of some of these layers. So if you go back to your slide, but basically you have the PM and the PMD. So they lie in the transceiver. And the transceivers can have many different types of wires coming out, as you might have seen. You could have copper coming out, you could have optics, you could have different medium. And that all is the thing is you don't want to burden the software engineers with this kind of detail. And so that's a good demarcation point for your switches or your other NICs or whatever you are doing in your software layer to kind of put the packets over the wire. And it kind of both physically as well as logically abstracts that out from the higher level of software.
Yeah, looks like they've done a great job, because if we lived for 30 years without knowing the lower layers, I mean, I peeled the onion a little bit earlier, but a lot of software engineers, they're able to do that abstraction and hide all that complexity. And I mean, there are problems as well as challenges that are solved at a lower layer and are hidden. It's a great design, I think. Maybe that's the reason it's celebrating 50th or it celebrated 50th birthday Ethernet last year. So. But it's a great design, I guess, right?
Yeah, yeah. And this is quite interesting because these are quite complicated designs.
Yeah.
Sending you guys, we hear in the industry copper versus optical. People used to say that copper is going to die at 10 gig. And look, we are now at what, 400 gig? And it's amazing amount of innovation. It's like communication theory, DSPs, equalization. I worked in that space for a number of years. Really complicated stuff. And it's kudos to the community and the engineering horsepower to keep innovating.
And yeah, I mean, I mean, somebody said that every year they say it's last year for Ethernet, taxes, death, and a few other things, but they don't go away. Sorry to put all of them in the same bucket, but it feels like that they keep going, right? So, I mean, again, thinking about software engineers and then guys who do Ethernet switches and routers, right? If you're operating at higher layer, when you have two entities talking, there is some control plane from a software point of view. Hey, I have to exchange some information so that we are on the same page, and then of course then we transmit data. So is there an equivalent like that on Ethernet itself? Are there control packets on Ethernet at that layer?
Yeah, yeah. So there are. And so what happens in Ethernet at this L1 layer, L1 kind of layer, is you send packets, right? But between packets, there are gaps. And in those gaps, you send a lot of control packets. And these control packets could be things like, okay, you want to figure out what speed you want those two endpoints to work at. So that's called auto negotiation or link training. And so there are these concepts called ordered sets where you might want to say, okay, the two parts have different kind of frequency or clocks that they're running at. So you might want to pause one frame versus the other. So all of those things happen. It's kind of control packets at a layer one layer, maybe not at what software people talk about, but it's very critical to have this. So there is mechanism within Ethernet to do that.
And because it's happening at that layer, we don't get to see, but magically your 10 gig connects to 100 gig or 400 connects to another 100 gig, and they magically negotiate all that using this.
Yeah. So that's all the control packets within the frames.
Makes
Mhm.
sense. Makes sense. Cool. Yeah. Thank you. So the other thing I always look, we can going back to like the information theory and other things we studied in school, right? So ultimately, I have some data. These are all ones and zeros. And then, how are they becoming like a fields and packets or symbols? I mean, how does that, I have a piece of data. How does it kind of go in to lower layers, and what happens there? Maybe you can share.
Right. So that piece of data, first you get to the MAC layer, which adds all of those delimiters like preambles and frame checking sequence and all that. Then they come to the next layer where you start saying, okay, I need to send this over a wire. So might need to encode it. What happens is if you get all zeros from the as a packet, then that's not good for the link. The link may lose lock, and a lot of bad things happen without getting into details.
Is it, sorry
So
to
you
interrupt, is it because you recover the clock, or you kind of get the clock from the data? Not, there's no like, they have their own clocks on both sides. Do you recover clock from that?
yeah, you recover clock from there because you need to make sure that you are able to detect the ones and zeros,
But
especially
is
at
there a
high speed.
local clock? I mean, how typically if you have a system, you will have a clock, right? There's some other, messages coming on the wire with their own clock. Between these
Yeah.
two, anything happens?
So you do have clocks, local clocks, but see those clocks may have different frequencies,
Yeah.
slightly different, right? You might have 100 ppm kind of differences, and the phase may be off also.
Mm.
So what happens is you get this data and you have local clock, but you need to move that clock a little bit. So that's called a clock data recovery. Yeah, there's a clock data recovery unit. Very complicated stuff, by the way. To do this as
Makes
400 gig, I don't know how component vendors do it, but it's amazing stuff. So anyway, so you need to kind of move that clock and kind of align it, and all of that has to happen. And so that's why you can't send zeros. You need to kind of code it, and then you need to kind of figure out whether you want to do different kind of modulation schemes. All of that happens, that magic happens in this layer one.
And if you're saying that if the packet is all zeros and it may have implications to the clock, then what if there are no packets on the wire, right? Then is there anything like, hey, this is the packet beginning and ending? How do you kind of figure that out?
Yeah, that's a great question. So what Ethernet does is it never goes, the wire doesn't go zero. You're
Mm.
always sending some kind of data, and it may be nonsense, but that's the higher layer of stack take care of that. You're just sending like ones and zeros, scrambled idle. It's called an idle ordered set. It's to
Mhm.
maintain that lock, to maintain so that when you send packets, then you don't have to retrain. It's already maintaining that state.
So idle also there is something going on. But is there
Yeah.
still something called a beginning of a packet or ending of a packet? Or I mean, it's idle, I'm seeing something idle. How do you just suddenly say, now what I'm looking at is a packet?
Yeah. So like I mentioned before, whenever you send frames, correct definition is frames because layer two and all that below that is just frames and
Yeah.
packet is above high.
Right.
So if you want to get pedantic, that's the
Yeah.
that's the right way to think of it. But you are right. So you send um, whenever a frame starts, you have a start of frame delimiter. So then the receiving end knows that I have the start of frame, and then you know when you have idle also in that same vein.
Because you may want to take this data from the frame and put it on some buffer or something like that, I guess.
Correct,
So
correct.
cool. So I also heard that this when we say let's say 100 gig link, it's not exactly 100 gig. There is a little more, right? Is it just the control packets, or what kind of things make the actual wire little faster? And then what else is going on to give? But I am getting 100 gig, but it looks like there is some more bandwidth out there.
Yeah, so that's a good observation. We talk about 1.6T Ethernet as an
Yeah,
example, right?
yeah.
That doesn't mean that the wire speed is 1.6T. Okay, the wire speed at the layer one could be 200 gig, could be 100 gig. The thing is, you just put more of them in parallel. So what happens is you have to distinguish between port speed and link lane speed, to be very precise. And many lanes make a link. Okay. So many lanes make a link which goes to a port. So if you have 1.6T, you could have 8 times 200, you could have 16 times 100, or you could have like 4 times 400. And that's one of the beauties of Ethernet, is with the same link speed or lane speed, you can actually make a bigger port speed.
And then so the SerDes are 200 plus 224 or 228.
It's actually
224 gig, right? So
yeah.
the 200 gig versus, is that where the extra thing coming from?
Yeah. So like I mentioned, the 200 gig might get coded up to 224 gig because you might put FEC into that. You might put different types of coding. And so even though it is 200 gig, because of FEC and all overheads, you might get to higher speeds. So the lane rate becomes higher.
That makes sense, right? Now, you mentioned FEC, right? Kind of talks about errors now. What kind of errors happen at each layer? Because this whole layered architecture is that each layer is taking care of certain kind of things that could go wrong, and packets get dropped, I'll retransmit at certain layer and things like that, right? So what kind of errors are happening at those layers?
Yeah, many different types of errors happen. Let me think. So you could have noise, you could have crosstalk, so that leads to bit error rates. You could have frame misalignment, like you have multiple lanes, you might have skew between these lanes. Um, you could have so those things, those frame misalignment can be easily fixed in the logic layer. Things like noise, crosstalk are more difficult to fix. You get bit errors, so you have to do FEC, you have to do CRC. Those are the ways the errors happen, and that's how you mitigate them at layer one.
And I mean, especially at UEC, right, Ultra Ethernet, the discussions, they are trying to do some link level retry and things like that. And, there are discussions about, hey, we are adding state to, state means, you're storing the packets. But even before that do you see those layer one or layer two as stateful? Like, how, like two endpoints talking to each other, do they maintain some state? How do you view that?
Yeah. So layer one is also stateful. You may not be aware of it because probably software at the software layer, you don't care about state at layer one. But to give you an example, when you have two endpoints and one is transmitting, you need to equalize. You need to you need to kind of maintain some, you need to maintain the state of like, hey, what are the, think of it as like hyperparameters of that link. Okay. So you storing the hyperparameters of that link. We talked about clock data recovery. You want to store the state of your phase, right? So it is stateful. The things you store are things which probably software engineers may not think about.
Yeah, and then sometimes they may think of state in a different way. This may be more state machine for them. State maybe, where do I put it in memory and use it or something like that, right? So the definitions change a little bit. So
Yep.
that's good, right? So yeah, like we talked about 10 gig. We even in this we mentioned right now we are in 800 gig, right? How, who decides, how does this just get faster? From 400 it became 800. Who did it? From 800 to 1.6, who defines it? What exactly happens there?
Yeah. So coming back to the original discussion we had, there's a forum, IEEE 802.3. So when companies decide that there's a market demand for higher speed, they will put forth proposals at different meetings of 802.3 and say, look, this is coming up. We need to come together to define a standard for that newer speed. And that's where the discussions happen and standards come out from that.
And then, like, so there, when the higher speed comes, is it somehow we have better DSPs or better they call modulation, encoding. I mean, how are they squeezing more into it? Or
All
maybe
of that,
all of the above, I guess.
all of that above. At this kind of speed, every everything counts.
Yeah, yeah.
You have to do everything to make that happen.
Yeah, from a simplistic software point of view, if you want higher speeds, can't I like on Highway 101, you want higher speeds, we say, hey, can you add one more lane? So is that also part of the deal that hey, you want higher speeds, you just put more lanes?
Yes, yes and no. I think what happens is that parts of the 802.3 um, forums just talk about like the line speed, right? But like I mentioned, you can make 1.60 with more lanes, right? Or you can add lower speeds, or you can go the other way also, correct? So what typically happens is initially when a standard comes up like 1.6T, then people say, okay, I'm at 100 gigs, so I'll put 16 lanes. But that's more costly, right? In terms of like lanes, number of lanes, and also then people say, oh, well, we need to go to 200 gig and we need to define a standard for 200 gig. Or we need to go to 400 gig. And then 3.2T comes. Then they say, okay, now we need to go to 800 gig. So that's typically the way it works. Um, yeah.
And so suddenly, if you have a new speed, how does I mean, we also work with old speeds, new speeds, and things like that, right? Can you shed some light on how I hear these gearboxes? Are these gearboxes really speed translation, or what exactly? How?
Yeah, mainly you're right. Yeah, at a high level, gearboxes translate speeds, right? Now, I think maybe hidden behind that is your question about like, okay, I might have a 100 gig and my other side maybe 200 gigs. So how does that whole thing work? So that's where auto negotiation, which I alluded to before, happens.
Yeah,
Like the endpoints exchange their capabilities, and the least common denominator is chosen by both of them, and that's when transmission happens.
cool, cool. Um, and so I mean, when we peeled this a little more, right? It looks like, my notion of a wire speed has changed. I used to think that, hey, there is a wire speed. We always talk about wire speed. Hey, is it operating at
Yeah.
wire speed? So now in this context, maybe wire speed means, I'm not going to say it's something else, but I may have to rethink wire speed because it looks like there is a higher speed, there is encoding, the additional control data is getting added, a control plane is getting added and whatnot, right? So wire speed, what does wire, maybe you can define what does wire speed mean to you?
No, you are right. I mean, this is a very subtle thing. So at a software layer, you might say, oh, I have a 200 gig link, correct? But like you also pointed out, you get coding. So it's actually not 200. You try to be as close as possible, correct?
Mm.
But because of the problems with like transmitting such high rate over physical media, you probably have to waste some bandwidth to kind of get to 200 gig, right? So at the software layer, you may not care about it because that's all handled. But just be aware that it's not as simple as what you might be thinking.
Yeah. But can we really get to packing? I mean, do we usually get close to ideal, like, pack with no idle gaps or packets are back to back? And do people get to true wire speed?
No, I mean, you always try to get there,
Yeah.
right? So you can do jumbo frames and things of that nature in Ethernet. Um, but you will never reach there. You will
Yeah.
always have some idle. You'll always have some preambles. It's there's some overhead always.
Yeah.
You just try to make it as small as possible. That's the
Yeah.
best you can do. Yeah.
Yeah. Um, you mentioned, I mean, it looks like there are a lot more things in Ethernet than at least a software engineer's view. You mentioned auto negotiation and some, link training, right? Are there any other features that are kind of prominent that higher layer guys might want to look at it?
Ethernet is very interesting, correct? You can actually, these are some good points, but then there are lots of activities happening to kind of make Ethernet more applicable to the AI world.
Yeah,
And that's a whole new topic, which I'm happy we can do a follow-up call
yeah,
about, like, say, ESUN, and then there's UEC, right? Then you can think about Rocky at a
higher
previous,
layer. Yeah.
right, at a higher layer. So it's a very fascinating field, right? And I encourage all the listeners and people on this call who look at this in the future to kind of just dig deeper and
Yeah.
feel free to reach out to me or anybody else that they know of. It's good if, like, the whole community understands the intricacies at every layers of the stack, and not just at the software layer or not just at the hardware layer either, because that's how we'll make more performant systems, lower the power, and just help the whole industry move forward.
We spoke about these higher speeds and AI transforming it, but earlier there is this Ethernet moving into vehicles, and it can connect my video cameras at home and things like that, right? So there is, it looks like a huge area there, and
That
maybe
is
set of
true.
features that may be different than what we are discussing.
That is absolutely true. Yeah, I've heard of those IEEE working at looking at in-vehicle entertainment,
Yeah,
Ethernet, right? Fascinating field. Just
power
amazing.
power is the
Power
other
over, yeah, there was like power over Ethernet, right?
Yeah. Your IP phone gets power over the thing was magic at one time. And crazy.
Yeah,
I
I know.
imagine, running around and one more cable. How many sockets do you have in your
Yeah,
desk, right? That was a big deal. I remember.
yeah.
Cool, fascinating. Thank you, Rohit, for insightful details. This is fascinating. We will come back. I know we try to kind of stay high level. We'll come back and based on questions. Maybe I'll open up to questions from the audience, anyone online, if you have any questions. Wait a minute. Yeah, if not, uh, okay, you're going 1, 2, 3. Okay, we're done. Thank you. Thanks, Rohit. This is very useful. We will try to get some feedback, and then what else folks want to know. If required, I may come back and trouble you again for maybe a little more detail on some topics, right? But really appreciate this. Thank you.
Thank you. Bye, everyone.
Bye, everyone.